Today's lesson is on improper integrals, and we are going to use the limit-taking process to evaluate certain integrals in this case. So there are two things that can happen for an integral to be considered improper. One is that if you're integrating on A to B, either A or B is an infinity, and it could be either positive or negative infinity. Clearly, if it were A down here and it were in numerical order, this would be negative infinity, whereas the B would be a positive infinity, again, if you're in numerical order. The second type of improper integral is when there's an infinite discontinuity somewhere on the interval from A to B. So, for example, what if this was the function 1 over x, and you were integrating from -2 to 2, then you would have a vertical asymptote at 0, and this would be an improper integral because of it. So infinite discontinuity just means vertical asymptote. So let's start by looking at a type 1 improper integral, and again, this is where one of the limits of integration is an infinity. We're going to start by drawing the graph of 1 over x squared, and we're going to draw it just to the right of the y-axis, so it's going to be here. And I'm not worried about the left side, and the reason why I'm not worried about the left side is because I'm going to integrate from 1 to t here. So here is the branch on the right side of the y-axis, and then I'm going to have a vertical line here at x equals 1, and I'll label that x equals 1. So I care about this function above the x-axis and to the right of the line x equals 1, and we're going to end the integral somewhere over here at x equals t. And I don't know what my t value is, but I'm effectively trying to find this area under the curve, this integral. Integral and area are the same since the region is above the x-axis. Trying to find this area from 1 to t of 1 over x squared dx. So if we integrate it, 1 over x squared integrates to -1 over x, and of course we evaluate it from 1 to t. By the fundamental theorem of calculus, we get -1 over t minus a -1, which is of course -1 over t plus 1. So what does the answer that you just found right here tell you about the value of a? Well, since t is a value greater than 1 over here on the x-axis, somewhere to the right of x equals 1, that means you have 1 minus some positive fraction. So the answer to number 2, and I'm just realizing it should say the answer to number 1 because this was number 1, what does it tell you about the value of a? Well, it must be less than 1. So now let's take the limit of our expression, the limit as t goes to infinity, of -1 over t plus 1. Well, when I plug in an infinity here for t, this is a rational function with a greater degree in the denominator, so this expression goes to 0, and my entire limit goes to 1. So what that means is, if my t value goes to infinity, and I integrate this function 1 over x squared from x equals 1 all the way out here to infinity, I accumulate an area of exactly 1. That's astounding, isn't it? Since there's not a bounded region here, and the x value goes all the way to infinity. So let's talk about the definition of an improper integral type 1. If we are integrating from a value for x that is a constant up through positive infinity, then what we want to do is replace that infinity with a t, integrate from a to t, and take the limit as t goes to infinity. If the limit exists, then this improper integral will equal the limit. Now, if I have the lower limit of integration equal a negative infinity, what I'm going to do is plug in a t for my lower limit of integration and then take the limit as t goes to negative infinity. The improper integral equals this limit, provided the limit exists. And then the last case, what if we had the integration from negative infinity to positive infinity? In other words, we're integrating across all real numbers. Well, you can split the integral at some x value a. Most of the time we'd split it at 0 because it's easiest to work with. And you would add up the improper integral here from negative infinity to a, which you would do by taking the limit as t goes to negative infinity, and you would add that to the improper integral from a to infinity, which you would replace the infinity with a t and take the limit as t goes to infinity. So if you can add the two limits that represents these improper integrals, you get the entire improper integral. So notice that we had said provided the limit exists. Well, if the limit exists, this improper integral is called convergent. For example, the one we just did, this limit exists and is equal to 1, and therefore the improper integral is convergent. If the limit does not exist, the improper integral is called divergent. So that would be a scenario when we're taking the limit and we get an infinity or a negative infinity here. So moving on to the next page, let's try another example. Let's take the integral of the function 1 over x from 1 to infinity, and let me show you how to set this up. You have to take the limit as t goes to infinity of the integral from 1 to t of 1 over x dx. So I have substituted in a t for my infinity and then taken the limit as t goes to infinity. Writing out this setup is critical, and you will not get credit on, say, a gateway or the AP exam free response if you don't set this up entirely. So now let's go ahead and integrate. So the integral of 1 over t is the natural log of x, and we evaluate this from 1 to t, which gives us the limit as t goes to infinity of the natural log of t minus the natural log of 1, which is, of course, 0. Well, what is the limit as t goes to infinity of the natural log of t? Well, that limit is infinity or does not exist. That means that this improper integral is divergent. So this is also astounding because think about the function 1 over x. Doesn't this look very similar to what we just drew on the prior page for 1 over x squared? We're taking this integral here as x goes to infinity, yet for 1 over x we find that this area diverges to infinity, whereas on the prior page, the exact same looking integral, but now 1 over x squared, as x goes to infinity, this area is convergent and is convergent on 1. There's actually a rule that guides when this type of improper integral converges or diverges. This is called a p integral because it's in the form of 1 over x raised to the p. This rule only applies for improper integrals of this form where you are integrating from 1 to infinity. These improper integrals will converge when when p, the exponent, is greater than 1, and they will diverge when p is less than or equal to 1. So we showed an example here where p equals 1, and we got a divergent improper integral. On the prior page, we showed an example where p was 2, so greater than 1, and we showed that the improper integral converged. Let's do one more example of a type 1 improper integral, this time with the lower limit of integration of negative infinity and the upper limit of integration of positive infinity. So what I need to do is set this up while pulling apart my integral. So first I'm going to have the limit as t goes to negative infinity, and I'm going to integrate from t, which replaced my negative infinity, to 0 of 1 over 1 plus x squared dx. I'm going to add to that the limit as t goes to infinity, and I'm going to sub in for my infinity a t value here, but my lower limit of integration is 0. So if you think about these two integrals, all I've done is taken the number line from negative infinity to positive infinity, and I split it at 0. I know that 1 over 1 plus x squared integrates to arctan. What I also need to know is what the graph of arctan looks like, and I'm going to remind you of this, and this is going to come up again and again in this course, so you really do need to know. Arctan has these horizontal asymptotes here at negative pi over 2 and at pi over 2. And of course, it intersects the origin right here, and it's always an increasing function that hugs its asymptotes as it goes to negative infinity and positive infinity. So why does that matter? Well, let's go ahead and do this integration. The limit as t goes to negative infinity of the integral of this 1 over 1 plus x squared is arctan of x, and I'm evaluating that from t to 0. And then my next integral is the limit as t goes to infinity, and again I integrate to arctan, and now it's from 0 to t. So if I go ahead and plug in, evaluate at 0 and at t, I will get the following. The limit as t goes to negative infinity of the arctan of 0 minus the arctan of t, plus the limit as t goes to infinity of the arctan of t minus the arctan of 0. Well, this is where our graph comes in very handy, because we need the arctan of 0, which is 0 by the graph. So this term arctan of 0 cancels, and this term arctan of 0 cancels. And now I'm left with the negative arctan of t as t goes to negative infinity. Well, as t goes to negative infinity, the y value of this function goes to negative pi over 2. So this expression here gives me a negative, the negative is from here, of the limit of negative pi over 2. And then this expression here, I need the limit as t goes to infinity of arctan. That's happening here, and as t goes to infinity, arctan goes to pi over 2. So I have the negative of a negative pi over 2, which is positive pi over 2, plus pi over 2 equals pi. So what they're saying on this function is that the area bounded by the function and the x-axis on all real numbers is equal to exactly pi. Now, I'm going to use this grid right here, even though it's not meant for this problem. This graph of 1 over 1 plus x squared looks like this. Oops. Goes like this. And it has an asymptote of the x-axis throughout. So basically what we're saying, what we just proved was that if you integrate this graph across all real numbers, you get exactly pi, which is astounding because pi is the ratio of circumference to diameter of a circle, yet it's also the area bound by the function and the x-axis of the function 1 over 1 plus x squared. This curve looks like a witch's hat and is therefore called the witch of Maria Agnesi, and the reason why it is called Maria Agnesi is because this is the mathematician who kind of labeled or named this curve at one point.